Hi everyone. I can see that we have 35 users, guests connected. Hi everybody. I'm Pierre Alliez from INRIA, Sophia Antipolis. I'm leading the Titan project team. Let me advance. So very quickly with the problem statement. So we assume we have as input a dense point set sampled over a surface, typically obtained by laser scanning. This is a very old scanner. Now we have very fancy data, of course. And the output is a surface that should be like an approximation of Earth in terms of topology and geometry. And that's the task of reconstruction, which is basically a conversion from points to a surface or sometimes a solid. And of course, robustness is motivated by these real-world problems in which the input is not really a dense point set. Okay, it's just a point set that is highly imperfect sometimes, with in terms of sampling, not uniform, anisotropic, missing data, uncertainty, and noise. And you can have a lot of different noise due to the acquisition system, and so on. So this is also an extreme case. You can also have outliers. Outliers is an example. This is a fish that was from the Sun King's flagship, sank off the Toulon coastline in 1664. And you see that during acquisition, there were fishes, there were a lot of mud. And so at the end, by photogrammetry, you get a dense, not so dense point set with a lot of outliers. So that also calls for robustness. So design properties for the surface is typically watertight, intersection free. You want also a good trade-off between fitting the data versus smoothness. And if you look at the problem statement, of course, this is an ill-posed problem, in the sense that if I give you a point set, there are, of course, many candidate shapes for the reconstruction problem. And this is, you can have, like, on the left, this is one hypothesis, in the middle, another surface, and so on. And this is really very basic and trivial explanation in 2D of what this is, but you understand, right? You can have possibly an infinite number of surfaces that pass through the shape, the point set. If you look at the literature very quickly, and it's a short talk, so in the main approaches you see, try to make a classification, you have so-called prior knowledge about what you want to reconstruct. So, and common priors are, I want to reconstruct a smooth shape, okay, on the left. Or in the middle, piecewise smooth, okay, like smooth away from feature and sharp at the features. On the right, that's a simple surface, right? Piecewise linear, for instance, that will connect the dots, and this is, of course, not relevant when you have noise or outliers. More sophisticated priors in terms of smoothness. There can be local smoothness on the left, can be global smoothness with a very global variational formulation with capability to fill all the holes and generate a watertight closed surface. And on the right, piecewise smoothness, and so on. So you have, in the literature, of course, you have a huge number of publications, more than 500 for sure. And you have a lot of different contributions for these priors. You have even priors that are specific to domains. So that's a publication I did with Florent Lafarge in my team on surface reconstruction by point set structuring, which is more relevant for urban scenes. On the right, also levels of details, not just reconstruction, but this time reconstruction with levels of details. Okay, that was work a couple of years ago. So now, this is the focus of today. Today, I would like to make a very short focus. This is not representative of everything that I did in the past on reconstruction. I wanted just to give you one small focus on our quest for robustness, okay? And of course, on the left, you see the perfect point set, the noise, outliers, non-uniform, blah, blah, blah. There are many categories of defects, and it's very hard typically to be resilient, namely robust to all kinds of data defects. But today's focus will be, what if you have a variable noise, where the level of noise varies on the scene? So let's go. In reconstruction, so what's the starting point? In fact, initially, I was using optimal transportation as a mathematical concept that is usually used for in physics, typically, or for physics problem, where you want to transport some mass, you want to minimize the cost of transportation, right? And based on that optimal transport notion, and mathematical notion, based on the Wasserstein distance, these people, Chazal and co-authors, they were able to compute from a point set a distance function, Unsigned, that is probably outlier and noise robust, namely such that you see these outliers here, this dot, outliers far away from the inferred curve here. You see the ISO levels of this distance function, they are resilient to noise and even resilient to outliers, okay? So that was a good starting point because they had a theorem they could prove, okay, under certain circumstances or conditions, I can prove the robustness. Let's start from that, okay? So we started from this robust distance function. Of course, noise outlier robust. We can efficiently evaluate this function. The cause of is that it was sensitive to variable sampling. You see that if you have a density like that, you can have this ISO level that stops here. Inaccurate at the inferred surface, because of course that distance function doesn't go to 0 exactly, you see, like that. This is a slice, okay, through the data. This is a point set in 1D, and you see this is my distance function, okay, based on the density of the point, in fact, and does not reach 0. So the first thing I did, I look at this unsigned distance function, and I thought, why not, instead of trying to orient the point set, namely to estimate oriented normals at each point, why not instead orienting the function? Okay, hopefully this will be more robust because that lives in R3, right, in space. So let's look at, suppose my shape is formed by these two nested circles in blue, okay? You make a cut through this shape here and you look at my distance function in red, okay? Function decreases, go close to 0, increases, and so on. You see you have 4 bounces, okay? What is, question for you, of course, now this is a robust approach we took that was published at SGP 2010, Symposium on Geometric Processing. It's called signing the unsigned, okay? Because we assume that signed functions are smoother and we want to reconstruct closed surfaces. Therefore, what we want to do is simply to sign this distance, okay? And among all possible ways to sign this distance, well, the best way to do it is indeed to find the smoothest function, the one that is signed like that, and that eliminates all these 2 bounces, okay? If you go down, you go up, you have a few bounces, fewer bounces. So another way, the best way to sign a distance function is to search for the smoothest function possible, and that is going to reconstruct the surface. So I'll skip the technical detail. We have a variational formulation and optimization, but basically we are signing the unsigned function that you see on the left in order to fill the holes like that and have something robust, or reasonably robust to noise and also to outliers. What happens now if we have a variable noise? Okay, there is a bit of applied mathematics now. So Chazal, he contributed this, again, this distance function to a so-called measure. What is a measure? It's a distribution of mass in space, okay? Now, I see every point set as a set of masses, and I'm going to rely upon the Wasserstein distance, which measures the cost of transporting the mass to a certain query point. So suppose this is my point set, sampled on the shape, okay? Mu is my measure here, and I have a query point Q. I enlarge the ball, I enlarge it until this ball encloses a certain mass, namely a certain number of mass of points, okay? And then I compute the cost of transporting that mass, simply the sum of square distances to every point to Q here, divided by M overall. And this is simply the Wasserstein distance, Wasserstein 2, because we have an exponent of 2 here, okay? That's just a concept of Wasserstein distance, but that translates trivially into something like sum of square distances to the points in the point set case, okay? So this function is great, but it requires a mass parameter. You understand that the larger the mass, the more robust the outliers we will be, but of course the smoother we will be. We will fit the data less accurately. So that's typically user specified, depend on the point set, that's global. So now, what about, it's not an adaptive distance function, because if I have a variable noise like that, if I consider my mass parameter that I call k here, k equals 6, okay? In that case, you see that my function, remember, along this red line, I cut through and then look at the distance function, okay? So here I'm closer to the high density area, farther away, closer. You see what happens? If the mass parameter is small, I will be sensitive to noise, okay? If k equals 70, I will be less accurate, namely I have a small shift of here, the minimum, okay, on the left here, but I will be robust to noise. So now that's the idea, the intuition behind this approach, is that we are going to look at how does this function behaves in accordance to this mass parameter and in accordance to the configuration of the point set locally. How am I going to do that? Well, suppose now I have not a point set sampled on a surface, but suppose that what I have is a uniform measure in D space. What does it mean? That means that in 3D, my point set is uniformly sampled. In other words, I am within the noise, okay? Within the noise level, okay? And suppose I look at this ball. If in that ball, the point is distributed like ambient noise, I skip the mathematical detail, but we can prove that the function behaves like a constant times the mass to the power 2 over D, where D is the ambient space, okay? And that means that this time, if for a query fix, this is proportional to mass over 1 over D, and that means it is decreasing for alpha greater than 1 over D. In other words, this is a function that is decreasing like that as a function of M, okay, this time. If I take this time D divided by M to the power alpha, okay? So now what I'm doing, I simply invent another distance function that I take it by D divided by M to the power alpha, and I will choose alpha appropriately, okay? I just construct a new function than the initial distance function. That's all. What else? The other case, suppose this time it's a submanifold. Suppose it's a uniform measure, namely it's a point set, uniformly distributed on the K submanifold. Suppose you are in 3D and that's the 2 manifold, okay, embedded. In that case, we can prove that the function behaves like constant as M to the power 2 over K plus H squared. And that means that this time we can invent a new function, D divided by M to the alpha. This time this is increasing for alpha smaller than 1 over K. Okay, so we can have a function like that depending on M. I guess you see me coming. What we did, in fact, now what do we want? Well, we want to devise a new function, a new distance function with capability to of resilience to variable noise. Because on the left, if the apparent dimension is 2 here, namely for this point set sampled in 2D, then that means we capture the ambient noise, okay? This function is decreasing for alpha greater than 1 over 1/2. Then if on the right, M is larger, take a larger ball, you see what is going to happen, that the apparent dimension will be 1, right? Now this looks like a curve now, okay? And this is like, it will behave like one submanifold in 2D, namely the function D divided by M to the alpha will be increasing for alpha smaller than 1. And of course, you understand that now I want to pick the function for which I have the minimum here in the middle. I will find the sweet spot, and in fact, automatically, I will search for all possible M, okay? And do that efficiently, such that we find the minimum of that new function, okay? And that is going automatically to trade off resilience to noise for fidelity to the data. What is intuition? We assume simply that it's a dimension prior, okay? Because we assume that the inferred shape, the shape we are looking for, is a submanifold of known dimension, right? That means what? That means for a K submanifold in D-dimensional space, our new function with alpha that must be within 1 over D and 1 over K, this is going to be our shape. And now if we instantiate that in 2D, then alpha must be within 1/2 and 1. And in 3D, if I search for a surface, it has to satisfy 1 over 3 and 1, between 1 over 3 and 1 over 2, right? That's all. That's enough for us to devise a function that behaves as we want. Remember, we want to find intuitively the smallest mass possible such that there is no oversmoothing, and yet we want M large enough so that the point set appears as a K submanifold. So at the end, that gives us a new function like that. You see, when this time, I have a function automatically that will decreases here, capture accurately the peak, also decrease here while being resilient to noise. And you see, I have no longer this sensitivity to noise. I will capture, and this is the optimal M, by the way, that we can display over here. You see that M really becomes very small here and larger here, okay, with a log scale. So at the end of the day, this was published at the Symposium of Geometry Processing, and based on optimal transport and a bit of applied mathematics behind it, we obtain, compared to the Poisson. Poisson is at the bottom row here. You see that Poisson, you can parameterize, give this the depth of the oak tree as a parameter, and you see that you need to choose, and basically it's a global parameter. So either you are faithful to the data. Here on the left, you are robust, but you are not capturing the data anymore, right? If you specify an accurate measure like that, then you are not resilient to noise, while our function sort of automatically adapt to the level of noise. This is still a small snapshot of the type of method we devise in my team. We try to devise methods with mathematical foundations with probably resilience to noise. What about recent work? This is my last one before last slide. So what about more recent work? You could argue that, okay, this was published in 2013. What about now? What are you doing now on reconstruction? And I will show you one recent work that was performed in my team at INRIA by Florent Lafarge and a PhD student. And this is called Kinetic shape reconstruction. I show you just one slide. This is just a teaser slide of the work of Florent Lafarge and Jean-Philippe Baucher, who was a PhD student. It's called Kinetic shape reconstruction. I was just trying to sketch by moving my hands how that works. It takes as input 3 million points like that. Okay, this is a clean point set this time. It requires to detect planar parts on this point set. And then for each planar part, each plane, if you want, is initialized at a convex polygon, okay, in space. Once you have a set of convex polygons, why is it kinetic? Because we make these polygons grow, let me enlarge. Every polygon is enlarging across time, okay, until it collides with the other polygons, okay? And we can control the number of intersections and so on. It's kinetic because it evolves over time. And we monitor the events, okay? At the end of the day, we generate a partitioning of space in 3D, followed by a graph cut optimization, and we obtain quite very good results, like only 1,500 facets for this mesh, probably watertight, and with a low number of facets. This is going to be presented at the next SIGGRAPH, by the way, very soon. And I want to thank you very much. Before I conclude, I want to show you, this is a survey on surface reconstruction from point set that we published a couple of years ago. And I also try to contribute as much as I can to the CGAL library, Computational Geometry Algorithms library. So some of the algorithms for point set processing, surface reconstruction are available in the library, not everything, of course. And we are currently adding more and more package, because the CGAL library for us, we try to contribute to this toolbox for both practitioners and academics and industrial users. And this all this work was funded by an ERC grant, followed by a proof of concept grant. Thank you very much.
Okay, thank you, Pierre, for the very clear presentation. So in case the audience has questions, you can put them in the chat and we can discuss the questions. Okay, I will start actually with a question. So the determination of M, this is a calculation per point, if I'm correct.
Absolutely, absolutely.
Okay.
So, and of course, that sounds not reasonable at all. And what we do, we first cluster hierarchically the point set. Okay. Mm-hmm. So imagine you cluster every point into clusters of, let's say, 10 points and 100, 1,000, and so on. Okay. such that while we search for the optimal M for every point, we have a very dichotomic search throughout a multi-level clustering of the point set.
Okay, and yeah, is there a possibility that there are multiple optimal M's per point, or sometimes it may not matter whether M is 20 or 21, but
yeah, so in fact, if you want, the way the function is defined, you divide by M to the power alpha, makes it like you have like typically a single minimum. You don't have really a large plateau, right? You don't have several ones, because well, depending on the distribution, it could be different, but no, typically like we don't observe any plateau or things like that. So typically you have only one, and it doesn't really matter indeed if it's 20 or 21. You can also compute an interpolation, but except for very, very, very small amount of noise. So there are also cases where you have zero noise, but remember the function needs a minimum. You need at least like 6 neighbors or so, right? Otherwise, you don't capture the surface.
No, indeed. Okay, then we have a question by Peter van Oostrom. How are larger data sets processed?
That's a good question. So, in fact, when we did this work, it was a couple of years ago, we were not scaling more than a couple of millions of points. It was not really made for cities. In fact, it was more like if you want for free-form shape, for statues and things like that, for closed object, because you understand this is an implicit method, right? So more like to complete missing data and generate watertight surfaces. But so for cities, remember I showed you another snapshot of the work that we did on levels of detail of urban scenes, and the latest work that Florent Lafarge did in my team. This latest work, maybe I can go one slide back. I cannot anymore. But this work is scaling much more. What we do divide and conquer indeed for this kinetic approach, okay? Then we split the point set into several point sets using standard divide and conquer. We do this kinetic partitioning, and then we glue together the reconstructions. And then we are scaling to several millions, but not at all yet to 100 million and 400 millions. And this is not yet in the Seagull library. So we are currently working hard on trying to deliver in a coming, hopefully in 1 year or so, a suite of algorithms in Seagull for levels of detail for urban scenes with Florent Lafarge and so on. So, but this takes always a lot of time to make this algorithm much more scalable. Indeed, that's on our agenda in terms of including delivering software components for Seagull. Yes.
Okay. Yeah. So in the meantime, I made you presenter again, so you may be able to go back in your presentation. Okay. But the next question by Ville. You can include external information to the weights, like intensity values.
Absolutely. Yes, I see the question. Absolutely. So in this optimal transport formulation, by the way, we have also another set of papers on using also optimal transport formulation. You're absolutely right. We can, if you want, incorporate the notion of reliability into a mass, the weight of a point, in fact, such that we give more importance to this point that have, let's say, high reflectivity and so on. Absolutely. We can really use that in this optimal transport formulation. I see another question. Advantage of kinetic reconstruction to combine the surface growing and piecewise planar reconstruction. Okay. For Cheyenne, I want to clarify that thing. I don't know if can I show a video or not? So just a 1 minute video or not?
Well, if the video is on YouTube or another.
No, I would need to share my screen. But in fact, Maybe I can do that by waving the hands. So just to make sure, Cheyenne, it's the kinetic approach. It's not a surface growing algorithm. It's not the surface. You are not growing on the surface. It's not that. We detect the planar parts. Then, okay, it's segmented, if you want, into planar parts, okay? Then, for each planar part, we compute a convex polygon, okay? That convex polygon, you take its center of mass, okay? It's coplanar with the polygon, of course. And then we enlarge the polygon radially with respect to that center of mass, okay? And that's the growing. It's just in the plane of that facet, okay? The only trick that we do is that we don't grow that forever. We grow it until we collide, let's say, only 1 or 2 or 3 times with the other polygons. And this way, it's perfectly piecewise planar. We obtain a sort of partitioning of volumes, polyhedra in space, combined with a graph cut optimization that will select a subset of the facet of this parsimonious arrangement, and then you get the output that you see at the bottom here. I have also a video of that, if you like. I could try to just share my screen for that. You will see how the maybe I try to share. Okay, I will let me. I can try to show you that. I will select a window. I need to select a window. Can I do that or not? Maybe I cannot. I need to select the entire screen. Is it good? All right.
It's coming, but the risk maybe that we cannot exactly follow the movie, but we can try. Yes.
Okay. You will see. You will see what happens. You see, we detect the planes, okay? And then every plane is growing, you see? It's growing. Not on the surface. It's really growing, and that gives you the arrangement, okay? That's the arrangement into convex cells. And then we cut through to get the reconstruction. And that's all, okay? Then I can stop the sharing of my screen.
Oh.
Okay. You hear me? I think I stopped the sharing, right?
Yes, yeah, that's true. Okay, one last question. You mentioned that the kinetic shape reconstruction probably gives a watertight surface. Why is it probably?
No, sorry. Then you are right, Georges. I think I mistaken. No. It's a probably watertight surface, right? Because whatever the point set we have as input, we take the bounding box of it, okay? That give you 6 planes, okay? Mm-hmm. We add these 6 planes to the kinetic framework, okay? And then it's that box that we slice more with the facet we detect. It's probably watertight because the way the graph cut formulation is performed, we can guarantee that it's watertight. Maybe I wanted to say probably watertight, not probably.
Okay. Yeah. Okay. Thank you very much, Pierre.
Thank you so much.
Let's hope we meet in person in October.
My pleasure.
We will see how the events will take place.
Yes, I hope to meet you there, and also to meet Cheyenne, of course, and Georges, and all of you. Thank you very much. Thank you so much.
Okay, thank you. In the meantime, we go to the next presenter, Professor Uwe Stilla, who currently has the presenter rights and the uploading seems to be okay. Yeah, so also Uwe is on the way. Excellent.
So, should I start?
Yes, you may start. Thank you, Uwe.
So my title is Change Detection of Urban Object using 3D Points. I have splitted my presentation because I'm not really clear if I'm really able to show both parts. It's a little bit more application oriented. And first of all, I want to show where I'm working here in Munich. You can see the window very on the left side. We have a lot of topics dealing with change detection using 3D points. From mobile terminal mapping, airborne terminal mapping, but also from ALS, airborne laser scanning, as well as mobile laser scanning. And these are current work of PhD candidates, and some of this work is already finished. So I want to pick out two examples: change detection of urban areas by ALS, means taken by helicopter, and photogrammetric construction site monitoring using BIM. But I'm not really sure if I'm really show both examples. Let me start with the first example with a pick out. Change detection using 3D points is a general interest of monitoring dynamic processes which show a confusing situation for human observers. Means when you have very extended areas and you should find out what has changed, so that is a little bit difficult and independent on the sensors, photogrammetry, laser scanner or radar. We are all working on the different sensors. The geometry of the urban structure is often represented by point clouds, and I will pick out two challenges: detection of small changes on the fly in extended urban areas showing complex structures, comparison between 2 point clouds, and the second example is change detection of objects of interest in a very rapidly changing environment. And so we have selected construction sites where there's a lot of movement and a lot of activities, and we want to find out what has changed. So I want to start with the first part, which was done with a PhD thesis of Markus Hebel, and very important is here that we have a helicopter which is looking in oblique view. Oblique view means that we have scenery and a laser scanner mounted outside the helicopter. There's also a little bit shivering this helicopter, and try to show you how that looks like when we are flying over a terrain of the TUM. That is about the velocity we are flying about the scene, and by the side-looking way, we have the possibilities not only to see the roofs, but also the facades. On the other hand, we have to say that we are, in this case, have in this case also shadows in our data. So when we are looking in oblique view, we have to fly multiple times. In this case, we have 4 flight stripes which have a cross flight, and this cross flight leads to 4 different point clouds. Okay, but the point clouds fits not exactly together, which is a problem, and this is due to the mainly caused by the inaccurate relative sensor position and also problems in the navigation data. So what we have to do for a change detection, we have first to do a co-registration, a very good co-registration. Otherwise, each error or each shift is a change, what is not what we want to have. That means we are trying to get phases which are stable, and for this we are doing classification of ground, vegetation, roof surfaces and walls. I'm very sorry that the animations are not working here on this big blue presentations, because I can only use here PDFs. Nevertheless, we take this planes from the roofs and we match the different flights, so that we have at the end what you can see here in a minute. Four flights which are now composed. Flight number 1 with the oblique situation. Flight number 2. Flight number 3. And flight number 4, now from down to top, which are well, adjusted. In total, when we are looking to this data set that we have then here, we see that color-coded from which direction the points were acquired. And you can see that is a little bit more that you have typically from the nadir view looking scans. Okay, here coming to the. So the basic idea is now for this work that we are able to generate a database like this, what you have seen before, which is not time critical. We use multiple scans for the relevant urban areas. The calibration is done. Just ICP is not working in this case. We have to calibrate the laser scanner. And we have the possibility of offline data processing, means we are able to detect phases from the houses, from the ground, and also from the vegetation, and means that we an analysis of the combined full point cloud at T1. So at a different time, T2, we assume that we have a mission, a helicopter mission, and we have an oblique forward-looking sensor, for example, for obstacle avoidance. We have degraded GPS accuracy, and what we want to use a scan line method, means we want to find changes on the fly, and this requires data alignment, and a terrain reference navigation is then also possible. These are just some simple steps. I'm not able to show here all the overlaid videos. We have a scan line. From the scan line, we are trying to find line segments. From the line segments, they are elongated to the break lines. And at the end, after we have such break lines, we are able to try to find these line segments which are looking downwards, because the main issue is to find here, which is not so easy, the ground line, means the ground, because we don't have in the line the possibility to find phases. After this, we try to set up from this lines stepwise during the flight phases from the building. And you can see here, number 1 is the ground. I'm very sorry that I'm not able to animate this. And number 2 is a phase which is on the side of a building, 3 on the top, and so on. But these phases are only used for co-registration, automatic co-registration. I'm also not able to show this video because this blue, big blue button is not accepting AVI files. When I go further on, then the basic idea now is typically when you have nadir views, you are doing interpolation onto a 2D grid, works best with nadir views, for example, for update of maps and comparison of point clouds. Other information is lost. In our case, what we want to do is the following. Beside the point, that we have from our obstacle or objects, we also store the point from where the beam was sent out. And that means when we have the way from S to P, we can say this is the way of the beam, and we can say this area must be empty. At position point P, we can say, okay, there is a reflection, and then after this, behind this direction, we can say we do not know what is behind that. That is a very important concept to handle, especially the occlusion, because we do not know in advance if a point was already seen or not seen due to the occlusion in the data set before. So typically for this, we are using occupancy grids very similar to 2D robot mapping, but we have here 3D grid cells for search operations especially, and so the cell size is comparably wide, and the occupancy is evaluated at the position at each laser point. There is no interpolation. The basic idea is the following: depending on our parameters, depending on the distance, means laser parameters, beam divergence, we are modeling a belief assignment for the laser point for the reflection. What we expect on the one hand, we have also this corridor we know that must be empty, and we have here an area we know that we know nothing about this area from the single laser points. So this formulation is given on the laser footprint, point, positioning, accuracy, and so on. The typical combination then of two observation is done by the Dempster's rule of combination, and we are using this belief masses at a position caused by a laser measurement, and so we are also able to compute the conflicting evidence for this. I will show this some slides later. So let us assume that the laser is fired from the helicopter, and we have a reflection in this cell P1. Then we can traverse this laser to the voxel and can say empty, 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 empty. We do not know, we do not know, we do not know. So when we have the conflict situation number one, we have a range measurement S, and we found this range measurement at time point T2, and we have measured, let me say 1 year before, that there are laser rays which have traversed this area. Then there is a conflict. So we have seen objects here 1 year before, so this must be empty. But in case now we have here a reflection, then there is a conflict. We call that conflict type 1. On the other hand, when we had a year before occupied areas by reflections, and now we are able to traverse this by a laser beam which reflects at Q, we have a conflict of type 2, a new range measurement traverses occupied space. By this two different types of conflict types, we can say on the left side there must be something which is new, and on the right side something is missing which was before. So an example, this was a flight about Abenberg, a small town in Bavaria, close to Nuremberg. We had a flight in 2008, 4 views and 5 million points. And then a year later, we had a flight in August 2009 and 1 strip south to north with 1.5 million points. And we can clearly see that we have a lot of type of 1 conflicts here, means due to the vegetation, because the year before it was in April, and in 2009 it was in August. What we are now trying to find is that we are this vegetation can be excluded, because in the first case at T1 we were able to analyze the point cloud. When we are now coming to the next slide, and I hope it is here, I want to show you the situation when we are flying over the terrain. In green, this is phases we know from the year before. In red, something is missing. In yellow, something is new. So when we go back to the presentation, this is 2008, 2009. I'm waiting for the slide. 2009, and we can see here our differences. When we go a little bit more in detail again, then we can see on 4 patches which are selected. This is the 2008 situation. Have a look to this area in front of the castle, have a look to the houses here, and also a look to this area. When we go to the next slide, then we have the same patches which were taken 1 year later. And the question now, what has changed? Difficult to remember. When we come to the details, then we can clearly see from the 2 slides. It's better to do that faster, but it's not possible with this system. I apologize for that. We can see that these houses are missing. We can also see that here were cars which are now missing. The flag has a different direction. Here we have a scaffold, and here have changes of this silage on these fields. So that is the output from the changes on the point level. And before I switch over to the next presentation, I want to mention that we have open access data sets. The last data set we published here on the website, which you will find in red, is TUM MLS 2016. And the day before yesterday, also the corresponding paper describing the data set is now available as open access. All the data sets here that we have. And for this, I want to show you one of the data sets which are taken with mobile laser scanning, can be used. This is a drive on around the TUM area, and you can see that we have a very high resolution point cloud, which is mapped here. We are coming to the main entrance now to our TUM when we go to the street left. And what you probably also can see behind, that is a dynamic point cloud. We see, for example, also pedestrian walking around here. And very important when you want to work with this type of data for learning, you need also annotated data, and this is available. We have labeled the data. I want to just to show you how that looks like in this presentation. These are the manual labeled data, are different classes, ground in yellow, blue are facades, the cars are in red, poles are in this more violet colors. Both data sets can be used for training of neural networks or other methods, machine learning methods. So I stop this video, and we have also here a reference list at the end with all the work we are currently working on. And I'm not sure how long is now the time. It's 20 minutes over, huh? Is that correct?
Just looking at the time, it's over, but I'm afraid we have to invite you again for giving the
so I think I skipped the second presentation. It's still on your server, but I think probably due to the time limitations, I have to stop here.
Yes, I think that's a good decision. So now, let's ask the audience whether there are questions on this part. Or as a starting point, I'm very interested in this labeled mobile laser scan data set. So I'm going to have a look at how to download this mobile and laser scan data set.
Important is if you have the web page here, you find all the links also on this web page. Also, the videos are here, a link on the web page. And we have taken a second data set in 2018. The same streets are mapped for this, and also we have annotated laser data. So in case you are interested to do change detection, what we are currently doing, it's very challenging. Then you can use both data sets. Also, the data sets from Munich, the flight over Munich, are available. Of Ambient data sets are available for change detection via this website. Okay.
And are you planning to use the same methodology of this this occupancy grid also for the MLS data?
For the what? Sorry, the last part.
Okay. Are you planning to use this occupancy grid also for detecting changes in the mobile laser data?
Yes, we want to do that, but just to explain, the resolution of the 3D grid, what was a question from Peter van Oosterom, is not critical, because this is just for accelerate the search operations. At the end, the rays are intersected by a corridor, and especially the parameters from the reflection means from the footprints are considered for the modulation. We are doing the same, which is now with mobile laser scanning, and 3 persons are working on that, PhD students. The names you will find also in the reference list. This is Mr. Gerung, Mr. Borgmann, and Mrs. Chu. All they 4 are working on that, and Mr. Yusheng Xu is working on especially modeling the phases with supervoxels and supergrids. I see a question from Peter van Oosterom. Is all the data stored at line segments with begin and end point? Yes, if you have a point. If you have a point from a laser acquisition, typically you have also the coordinates from where the laser comes from, and this is also provided here in the test data sets, so that you can really have the ray between the shot and the object in between. Also begin point and end point is given here, and I think it's very important, especially to handle all the occlusion purposes. and occlusion problems. Is there any other question?
Okay, this seems not to be the case. So the presentations will be online afterwards, also the recording of this session. And also for you, I hope we see each other in person in October during the PhD Defense of Cheyenne. And yeah, on behalf of the NCG, so the Dutch Center for Geoinformation and Geology, I would like to thank both speakers again for the willingness and efforts to do the presentation in this online mode. And we realize it took more time to prepare and to do the presentation, but we are very glad that we still could have this seminar on point clouds within the Netherlands, but also within Europe. That there was a large interest in this seminar, and yeah, we are very happy that we could have them in this situation. So
thank you very much for the invitation to give a presentation.
Thank you so much. Yes, it's a pleasure.
You're welcome. And okay, if there was an audience, there would be a lot applause. Okay, now it's a bit empty, but okay. Thank you again. And
thank you very much.
Okay.
Have a good day, everyone.
Bye-bye.